How are you doing?
I'm okay. How are you?
I'm well. If you were on a talk show, how would you have me introduce you?
Okay, so if you're going to introduce me, I'm Tommy Ratliff, a professor of mathematics at Wheaton College in Norton, Massachusetts.
So, Tommy, um, why did you choose to pursue math in the first place?
So I've kind of always been interested in math, even from when I was, a little kid in elementary school. I always liked math and always did well at it. Um, in college, I was essentially a double major in math and computer science. At that point, there were very few places that had computer science straight majors. And I actually started in CS grad school. So I started in computer science grad school at um, University of North Carolina at Chapel Hill. But while I was there in my first year, I realized that I kind of really missed the abstraction of mathematics, and I kind of missed the permanence of mathematics, meaning that once you prove something in math, it's always true, right? It's like in math, the stuff that Euclid proved 2,000 years ago about geometry is still true, whereas you don't find a lot of ancient Greek biologists or ancient Greek chemists whose work is still used. And in computer science, a lot of what was interesting at the time was kind of dependent upon the current state of technology and the computing power. And so for some people, that's really exciting. Stuff's always changing. But for me, I kind of liked the sort of the longer term view in mathematics. That just kind of appealed to me more kind of in my own sort of intellectual bent. And also, I decided that I really wanted to teach because I had gone to a very small school and really liked interacting with undergrads, and decided I'd rather teach math than computer science. So then I ended up switching to math grad school and ended up at Northwestern.
Interesting. So, what's one aspect of math that you didn't think you were getting into, but once you were fully invested, you realized, okay, this is it?
Um, so I had kind of a little hint of this from an independent study I'd done as an undergrad, but the thing that I had really kind of underestimated is the um, importance in writing and communication in mathematics. Because, there's lots of really, really cool ideas out there in math and lots of really cool, computations and proofs you can do. But unless you can explain to people why it's interesting, they won't care. And then what you do is not going to be, and then what you do is not going to be viewed. Well, it won't be important and it won't have an influence. And so, because, the idea is you're developing really kind of, hopefully deep ideas, and people are busy. If people have to dig too much just to understand what your point is, then they're not going to care. So to me, kind of the time that it takes, even after I've got the mathematical results, to write something up well and explain it well and realize what it's like to someone who is not completely and totally invested in this problem, for someone coming in from the outside, that's the time to explain that is the thing that I'd kind of underestimated.
That is that is very true. I I feel like I encountered the same thing doing a different project though, not math, but what you said about communication is definitely true. So, yeah, I know a lot of professors like do research on the side. So, do you have any research that you're currently doing and what would you say about it?
So yes, so I've got uh, a well, really one kind of active project going on and another one that I'm trying to wrap up. So so a little bit of the background for me. I did my graduate work in an area of math called algebraic topology, which is a very kind of very abstract, I'd say really very, very beautiful area. But it's also something that it's hard to talk to undergraduates about, or really even my colleagues at Wheaton. So I kind of branched into other areas. And for the last couple of years, I've been working in an area with a group of mathematicians and geographers and lawyers who are looking at issues in the United States around questions on redistricting and gerrymandering, which is basically, the idea of gerrymandering. There's kind of a long history of it in the U.S., which is where we have single-member districts in Congress or in state legislatures. And so the party in power tries to draw the maps, the districts, to benefit them. And so then the question is there a mathematical way to look at a districting plan and say this is unfairly gerrymandered? And so what's really interesting about it is it pulls in, it's not just questions about geometry, because you can look at some of these districts that look really crazy and say, oh yeah, that's outlandish, right? There's one, I think it's District 7 in Pennsylvania, that people have labeled the Goofy Kicking Donald district, because you can draw an outline on it and it looks kind of like Goofy kicking Donald Duck. Okay, so there are these outlandish shapes, but it's not just about the shape. It's also about where people live. So it's about the political geography as well. So you need the geographers and the GIS experts to then pull in the data. So you have both that information as well as the geometry, and then trying to develop a metric. So the project I'm working on right now is trying to come up with a metric that uses some of the computing tools that have been developed in the last few years to then get a better indication of whether something has been, kind of completely unfairly gerrymandered.
Excellent. And you talked about some of the other people who are not mathematicians working on your team. So could you expound on the type of team that you work with?
Okay, so the team I'm working on this project with, they're actually two mathematicians. One is at St. Mary's College in Moraga, California. The other is a mathematician at San Jose State. But we met at a conference in San Francisco last year. And this was a conference that was sponsored by the Metric Geometry and Gerrymandering Group, which is a group at Tufts and MIT, and sponsored by the Lawyers Committee for Civil Rights Under Law. So for this, there are lawyers who were formerly worked for the Justice Department, law professors at University of Chicago, at a couple of law schools in California. And so the two people I'm working with, we're pulling in the work that these other groups are doing, and we're working with them closely. What's happened is there's been a whole lot of activity in this area lately, and we're trying to fit into one piece of it because there is a lot of activity, because in the US, there's the census coming up next year, which counts the distribution of people in the country. And then every district will be redrawn in 2021. So we're taking the work that this group up at Tufts and MIT is doing, some of their computing tools, some of the data they're developing, trying to develop our own metric, and we've been in contact with them about sharing with them.
This is like my favorite question. Is there a good foundation for a math undergraduate degree? And if so, what is it?
Okay, so that is, that's kind of, well, okay. I will give you the whole spiel. Okay. So I think mathematics is so broad. It's such a broad area that there is not a one size fits all foundation for every student. Okay. And one reason I feel kind of confident saying that is the professional societies at various times, the American Mathematical Society and the Mathematical Association of America, have tried to come up with, here's the best curriculum for an undergraduate math major. And they've essentially said, okay, there is no just one core set of courses that everybody should take. So what I would say is, so I kind of feel like in the past, it used to be pretty easy that you thought of math falling into two camps. There's kind of the pure abstract math, and then there was applied math, which tended to be things that were driven kind of more by engineering questions, okay, and engineering, and examples from kind of the hard sciences. One of the things that I think has changed lately is there's a lot more interesting questions and applications involving perhaps topics from discrete math and topics in computing, where computing lets you, gives you access to questions that you couldn't necessarily answer before. Okay, so that's a long spiel, which probably a little bit off topic. But what I would say is, if you're looking for a foundation as an undergrad, kind of the big things that I think of are some background in what I would say are discrete math topics. So by that I mean like linear algebra, graph theory. Also, statistics is just more and more important. No matter what you're going to do, you're going to be dealing with data and dealing with some type of data analysis. So I think some type of statistics. And then also have some experience coding. You're going to be using computational tools kind of no matter what you do. And then the last thing is, I would say, take an area that you're really interested in and study it in depth. So by that, I mean a sequence of 2 or 3 classes in a particular area. I think the experience of getting in depth and really kind of understanding a particular area deeply then ties over later, because I think it's impossible to predict what specific knowledge you're going to need. But if you have the experience of studying something, really getting deep into one topic, then you'll be able to repeat that and apply that in other areas later.
Yeah. Does calculus count, or is that just like foundational for everything?
I kind of think of calculus as almost kind of foundational.
Okay. There goes my pride.
No. I mean, it's important, but in some ways, it's kind of like, algebra is important. Being proficient at algebra is important. But the ideas of calculus are kind of it's one of the steps towards mathematical maturity.
I see. So what are some of the ways that students can build on their skill sets? Like, what are some activities that students can participate in? Or what are some tricks that you have for students to build on their math skill set?
I think one of the most important things is to seek out a peer group to work with. Because I think talking about mathematics, talking about the ideas, and then trying to take what you learn from your peers and writing it down and expressing it in your own words is the thing that really helps you not only clarify your own thoughts, but clarify your own thought process. Okay. And connected to that is any opportunity you have to give a talk about mathematics, do it. So there are, these days there are lots of undergraduate math conferences. And students give talks at these conferences, and many of them, it doesn't need to be on original research. It can be on, students give talks on, here's something interesting I saw in a class that you may not have seen. All right, so the opportunity of then taking a topic, thinking about how you would present it to somebody else is really, I think, is really valuable. And nothing quite like the fear of standing up in front of other people is kind of a big motivator. So in general terms, that's what I would say. It's really about working with other people. And as you're doing that, think about how what you're studying ties in with things you may have seen in other classes. So one story along those lines, I had a student who was an education major. She came to see me when she was taking her senior seminar in education, and she said, "Oh, I'm so glad I was a math major. It's helped me so much with my writing." She said, talking to some of my, some of the other students in the class, I'm thinking about how I want to write this paper. I already know what the argument is. I know what the logical flow is. I know what follows logically, and I kind of have the overall structure in my head already. I've got the bones. Now I just need to polish it, to get the prose down, to make sure it fits. So her comment was that her mathematics really helped her think about kind of her clarity of thought when she's presenting arguments or writing papers in other contexts. So so I'm kind of a firm believer in this idea of mathematical thought as a way of life. So for suggestions for within a specific class, I would say it's related. Find a peer group, seek out a peer group within the class, and also, take advantage of your faculty. By take advantage, I mean go to see them during office hours. I don't mean unfair advantage, right? So, and it's very easy to get lost in the kind of in the day-to-day. What do I have to do for tomorrow? Every so often, leave the time to step back, take a breath, and say, okay, what's the point? What's the mathematical point? How does this fit in? What is the big picture? And if you don't see the big picture, ask other people, talk to other people. Well, and so one other thing to add to that is, one of the sort of truisms is, if you want to really learn something, teach it. Right? So find somebody like this, a friend in the course before the one you're in, and try to help them where you can, and that will really help you clarify your own thoughts.
Yeah, true. So I don't know if you've touched on this, but I will explicitly ask the question. So, what advice would you give anyone who's considering taking an undergraduate degree in math?
So, I would say, if you're interested in it, give it a shot, right? Take the next class. See how it goes, right? That's the that would kind of be the first thing. The other thing is, just because or if you major in math, that doesn't mean that your career goal is that you're going to be a mathematician. That's not the only thing you can do with a math major. Okay. So if you're hoping to do something in your career that involves math on a daily basis, then there will be future schooling in your, in your life plan beyond your undergraduate degree, right? There'll be grad school of some sort. But I would say, math is also a great complementary major to pretty much anything. So, at Wheaton, we're looking back at this, and something like 60% of our math majors are double majors. Some of them are in things you'd expect, like, computer science or chemistry or physics. But there's also philosophy, English, Hispanic studies, French studies. And, we've had students with math majors go on and, go to med school, become nurses, work in the finance industry. So, what I would say, kind of the gut feeling is, if you're interested in it, keep taking the classes and just, and just see where it leads you.
Thank you. Thank you very much. Tommy, if you could go back in time, I don't know how many years back that would be, but to your just saying.
It would be a few.
Just a few, not too many. If you could go back to your undergraduate days, what advice would you give yourself looking back at it now?
So there are, first off, there are a few things that I think I went very well for me as an undergrad. Okay. So I went to Rhodes College, which was a small liberal arts school in Memphis, Tennessee. And, as far as my math career goes, it was an environment where, most of my upper level classes had fewer than 10 students in them. I ended up taking I did several independent studies, including one of which ended up leading to a project that ended up being published in an undergraduate research journal. Okay, so I really got the experience of working closely, kind of one-on-one with faculty, which really prepared me very well for graduate school and kind of understanding what sort of the independent learning process is like. So that went well for me. I also took a bunch of classes in different areas. I really enjoyed like my literature classes I took, because I kind of realized I wouldn't read Faulkner unless I was actually taking a class in it. And so that was fun. I knew I'd never think deeply about romantic poetry unless I took that class in Wordsworth and Coleridge. And so so those are things I really enjoyed. I'd say the one really kind of sort of biggest regret I have as an undergrad is that I didn't develop a fluency in a second language. And so I think that's kind of that's been kind of, as I've gotten older in particular, I've felt that that's kind of limited me somewhat in terms of, the perspective, having a broader perspective on the world and understanding where, kind of the backgrounds of just from, the world's a big place. And I feel like I've kind of had blinders on only being fluent in English.
On the previous question, you did talk about, you talked about not looking at being a mathematician as your final option if you take math as your degree. So what's the most interesting path? Interesting is subjective, of course, but what's the most interesting path you've seen math majors take?
one one sort of unexpected path is one of our majors, after she graduated, got interested in statistics, in particular in epidemiology. And so she is now working as an epidemiologist for the New York Fire Department. And so what's interesting about that was they realized after 9/11 that they were not tracking health outcomes of firefighters who in particular had fought fires in buildings in New York City, where when you're in a fire in a building in a city, you're exposed to potentially, fumes from whatever is in the building materials, from cleaning products that are in the building. And so there are different health outcomes that potentially affect firefighters in an urban area compared to firefighters elsewhere. So I just thought that was kind of an interesting, sort of an interesting use of math. And another one of our students who ended up, she was a double major in math and philosophy and got a PhD in philosophy, but she got her PhD at Carnegie Mellon, which is a very technical oriented school. And one of her comments to me was she kind of wishes she had had more statistics as an undergrad for her philosophy degree, because they do empirical ethics there, where they actually do studies and try to see how people will respond to things. So I thought that was very interesting. And actually, she is now working at Tufts and in some way associated with this gerrymandering group as well. So she took a course from me in voting theory, and she'd also been very interested kind of in political philosophy and in voting theory. So this also kind of fit in with her background there.
Cool. So for my final question, who inspires you to be a better mathematician?
So I think for me, the most obvious answer is my students. In that, if I think about, what I'm trying to do every semester as a professor is, the goal is to challenge my students, for them to ask them to stretch themselves, to think in new ways and take risks, take intellectual risks and perhaps get out of their comfort zone. And if I'm asking, rooms full of students to do this every semester, I should ask that of myself. And so part of that then means, branching out and trying to look into areas that I haven't worked in before. It's like that's partially where the interest in kind of the path and voting theory, as well as this work into the gerrymandering world, came from, is trying to just be intellectually honest and apply the same filter to myself that I apply to my students every semester. Another bit of kind of explicit advice I would give is that, something to remember in studying math is that it's going to be hard and it's going to be sloppy at times, because the things that you are learning are difficult concepts, right? I mean, the calculus that you learn in in 2 semesters of calculus, that material wasn't developed in the 9 months that you're taking those classes. That material was developed over hundreds of years. And so you're seeing kind of the most distilled version of it. Your learning of it, it's going to be sloppy, it's going to be frustrating, it's going to be 2 steps forward, 1 step back. But by struggling with it and then putting it all together, you've got you'll have an understanding at the end that is that's much better than you think it's going to be along the way.